Hello, music nerds! I'm back with Chapter 4 of Hermann Helmholtz on the sensations of tone. The link to the web book that I'm reading from is in the description. You can find the entire text of the book there, as well as all of the apps that I'm going to show you in this video, so let's get to it! Chapter 4, on the analysis of musical tones by the ear. Last chapter, we were looking at the upper partial tones using sympathetic resonance. In this chapter, we're going to prove that the ear does that on its own without the help of any resonator. Now, he does acknowledge that it can be challenging to hear upper partial tones if you've never tried to do it before. So he gives us some tools. First up, the odd upper partial tones are easier to hear than the even ones, because even ones are octaves either of the prime tone or of an upper partial close to it, and octaves are harder to hear than other intervals. If I play a C chord with the fifth and without the fifth, it's easier to recognize than if I play a C chord with the octave and without the octave. So if you're trying to hear an upper partial tone, listen for the odd ones. The second tip he gives is to play the tone you're trying to hear before you try to hear it. So if I'm trying to hear the upper partial tones of a C, I'm going to play the third upper partial, the G, for me to hear first, then go back and play the C. If you're still struggling to hear it, try it with earphones. Hearing upper partial tones in woodwinds or the voice is harder than hearing it in strings, but it is possible, basically doing the same thing, bringing your ear's attention to the note. For a voice, have someone sing an E flat, then play the third upper partial on the piano. As it dies out on the piano, you'll still continue to hear it in the voice. Or you can use resonators. If you play a C on a woodwind and have a resonator tuned to G1, you'll hear that G really strongly when the resonator is in your ear, and hopefully you'll still hear it weakly when you pull the resonator out. We now proceed to prove that the human ear really does analyze musical tones according to the law of simple vibrations, or at least to proving that when an analysis of a composite tone into simple vibrations, affected by theoretic calculations or by sympathetic resonance, shows that certain upper partial tones are absent, the ear also does not perceive them. Now for this, we need to remember about nodes on the harmonics of strings. So here's our string vibrating in its prime tone. Here's the first harmonic. It has a node right here in the middle of the string. Now if we pluck the string at that harmonic right in the middle of the string, we're not allowing it to be stationary in that position, so we won't hear this first harmonic. And in fact, we won't hear any harmonic that has a node in the middle of the string. And we can try it on a virtual string. When I move this red dot, that's where I'm plucking the string. So if I pluck it from right here, we should hear all the upper partials. But if I pluck it from the middle, we shouldn't hear any of the evens. And so on for all of the nodes of this string, which are marked by little gray marks here. The same kind of thing is true in reverse. If we touch a vibrating string gently for a moment with a finger or a camel's hair pencil, we damp all those simple vibrations which do not have a node at the point touched. Those vibrations, however, which do have a node are not dampened, and hence will continue to sound without the others. Let's try it with our virtual string. Pluck it down here and damp it right in the middle. Let's try again with the thirds. Oops. Now if I pluck it right here in the middle and then dampen it in the middle, it should be silent. Ooh, that's high. Okay, then he goes on a little bit of a tangent, talking about the difference between how the eye perceives a plucked string and the ear perceives a plucked string. This is a figure of images of all the motion that a string goes through when plucked. And this graph shows the amount of pressure on one end of the string affixed to the bridge as it goes through each of these stages of motion. We cannot but feel astonished that a motion produced by means so simple and so easy to comprehend should be analyzed by the ear into such a complicated sum of simple tones. For the eye and the understanding the action of the string on the sounding board can be figured with extreme simplicity. This is one of the most striking examples of the different ways in which eye and ear comprehend a periodic motion. Then he moves away from strings and into other sonorous bodies which are a little bit more challenging. In most other cases, the mathematical analysis of the motions of sound is not nearly far enough advanced to determine with certainty what upper partials will be present and what intensity they will possess. In circular plates and stretched membranes which are struck, it's theoretically possible to do so, but their inharmonic secondary tones are so numerous and so nearly of the same pitch that most observers would probably fail to separate them. On elastic rods, however, the secondary tones are very distant from one another and inharmonic, so they can be readily distinguished. Even for sounds that we cannot analyze theoretically, he still uses resonators or other sympathetic vibrations to compare to what you hear with the ear. By the above experiments, the proposition enunciated and defined by G.S. Ohm must be regarded as proved. The human ear perceives pendular vibrations alone as simple tones, and resolves all other periodic motions of the ear into a series of pendular vibrations, hearing the series of simple tones which corresponded with these simple vibrations. Then he clarifies some terminology stuff for the rest of the book. A musical tone is the sensation excited in the ear by any periodic motion of the air. A simple tone is a simple pendular vibration. A compound tone is the sensation of several simple tones, and a composite tone is produced by several musical instruments acting at the same time. At this point in the chapter, he addresses some of A. Seebeck's issues with Ohm's law, but a modern audience, we kind of all agree that these upper partial harmonic tones exist. But there is a cool app here. You can draw a function, and these springs are tuned to the first 5 harmonics of the sketched function. The bottom spring is tuned to resonate at a frequency corresponding to a single period of the function, spring above 1.5, 2, 2.5, and 3 times the frequency. So let's draw a function. Now this is certainly not a simple pendular vibration, but each of these springs does create a simple pendular vibration. Let's try another. That's kind of mesmerizing. All right, his next experiment is with this glass jug here, and he's got a piece of pipe that's sort of flattened at one end, and to the other end of the pipe he would attach a bellows to blow air across the top of this bottle and create a tone. And of course you can fill this bottle with water or oil to change the pitch of the tone. I tuned a large bottle to be flat and a smaller one to be 1 flat. On producing the upper tone first and then letting the lower sound with it, I found that I at first continued to hear the upper tone with its full force, and the undertones sounding below it in its natural quality of oo, as in two. But by degrees, as my recollection of the sound of the isolated upper tone died away, it seemed to become more and more indistinct and weak, while the lower tone appeared to become stronger, and sounded like O in toad. Although the pitch of a compound tone is, for musical purposes, determined by that of its prime, the influence of the upper partial tones is by no means unfelt. They give the compound tone a brighter and higher effect. Simple tones are dull. When they are compared with compound tones of the same pitch, we are inclined to estimate the compound as belonging to a higher octave than the simple tone, or to hear a different vowel sound, like with the jug. The last thing he talks about in this chapter is the difference between perceiving synthetically and analytically. Perceiving synthetically is the lower grade of consciousness. We are aware of the influence the sensation has on us. Perceiving analytically is the higher grade, where we can distinguish the sensation in question as an existing part of the sum of sensations excited in us. In terms of sound, perceiving synthetically would be being able to hear the difference in quality of a simple tone and a compound tone, whereas perceiving analytically would be being able to hear all of the simple tones which are a part of the compound tone. Now, he makes some interesting analogies with the other senses here. For taste, you wouldn't expect every person to be able to taste a recipe and know exactly the ingredients that made it up. For touch, if you touch some cold metal, you might perceive it as touching something wet because it's smooth and cold, and wetness we perceive as a combination of smooth and cold. And of course, sight. Every color we see is made up of red, blue, yellow, but we don't see it as a composite of red, blue, yellow. We see it as purple or green or whatever it is. So let's finish off this chapter. The result of the preceding discussion may be summed up as follows. 1. The upper partial tones corresponding to the simple vibrations of a compound motion of air are perceived synthetically even when they are not always perceived analytically. 2. But they can be made objects of analytical perception without any other help than a proper direction of attention. 3. Even in the case of their not being separately perceived because they fuse into the whole mass of musical sound, their existence in our sensation is established by an alteration in the quality of tone, the impression of their higher pitch being characteristically marked by increased brightness and acuteness of quality. In the next chapter, we shall give details of the relations of the upper partials to the quality of compound tones. So be sure to subscribe so you can see me next week with that chapter. And if there is anything in this chapter you want to read in more detail, or if you want to use the Plucked String app, particularly if you don't have a stringed instrument at home to experiment on, go to sensationsoftone.com. I'll see you next week. Bye!